thank you all for your patience, and my apologies for my rather awful internet connection. So, what I'm going to do is very briefly, and I hope simply and clearly, pick my way back through what I was trying to say. So I'm going to not linger too heavily on some of the concepts. We've got a slightly laggy screen. So the question I asked is, how does the brain, or how does to say that the brain learns is, I think, a slightly odd and rather dumb question, because you and I learn, and the brain undergoes and takes processes, right, which underlie the process of learning. Okay, so we learn, but the brain has these processes. So one of the ways that we think about this, when we look at learning, is we have this idea called a concept map. And I'll wait for that screen to catch up. So a concept map is, if you think of this dot as a concept, and this is another concept, and this is another concept, we have all kinds of different concepts. So through your previous study, you have a whole range of a number of different concepts. The process of learning is linking them together, for example. And the really interesting element here is, let's go that way for that one. It doesn't matter, it's an abstract picture. When you learn something, you basically develop a map of the connection of concepts. But what is that connection? What is it? What is the brain actually doing? Does it literally draw a wire between different concepts? Does it, what does it do? Okay, so what does the research say? Well, in the lecture, I very briefly mentioned analogy, but I'm going to sidestep that for a minute, and I'm going to talk more specifically about what is this relationship between one concept and another, and how does it help me understand what learning is? Well, strictly speaking, learning is this process. Okay, part of the research that I've been involved in uses neuroscience, cognitive science, philosophy, psychology, the humanities, computer science. And out of all these disciplines, what the research has shown us is that this simple formula effectively defines what understanding and learning is. Okay, so when we say we learn something or we understand something, this pattern is always involved. Okay, now this comes out of research that I've been doing for several years, and the notation is going to be unfamiliar because it's based on what my own work, my own rendition. So what I'm going to do is translate it for you into normal language. So what we have are conditions, situations, contexts, to which we respond, and that gives us your object. Okay, now again, that's really quite simple. I just shift the paper over so you can see that. So I need to spell this out for you, and then I'm going to very briefly say, how is it an advantage knowing this to help me learn, right? What Nad are you talking about? Okay, so the concept map here on the left hand side is quite straightforward, but the relationship between concepts is not some kind of line you draw between them. One concept literally provides the context for another concept. And that abstract idea boils down to pretty much everything that goes on with the brain underlying the process of learning. and understanding things. So if we look at ordinary, very, very ordinary processes, and what we're going to do is we are going to argue that these very ordinary processes of understanding are directly involved in the process of learning anything. Okay, it's gone out of focus. Let's get that back into focus. Give it a second. Okay, so that's quite a big statement, because my argument is very simple. If I can get my head round how the brain and how learning takes place in anything, then surely if I approach the subjects I have to learn and I use this relationship as a tool, it will accelerate my ability to understand what I am trying to understand. Now, the only problem here is that this might make everything so simple that you fall into a false sense of, oh, then everything is really straightforward and it's easy to understand. No, difficulty in understanding comes from complexity, from abstract nature of things, from unfamiliarity. So there's still work to be done, but this pattern of ordinary understanding, which is encoded in these types of images and this type of notation, I'll let it catch up, right, is where it's a huge advantage. So let's say that we're trying to understand a subject, right, an object. We've been taught that object in a lesson, right, and the lecturer has said a ton of different stuff about it, and you think, oh my goodness, how am I going to get my head around that? What does that all mean? And then they start talking about that, and then they go on to talk about something else and talk about something else. So the very first thing is, I need a strategy to tackle how to understand that particular object. Examples here are very, very useful. I don't want to put off the people who don't do programming, so I won't use a programming example. I will use a very, very simple, banal, ordinary, everyday concept. And then we'll use a scientific one, and then we'll move into computing, right? So we'll come back to our famous character here. This is Bob. Okay. And Bob isn't very happy. You just bump into Bob one day, and Bob frowns at you and then walks off. Right. Now, Bob is a very good friend of yours, so you're initially perplexed. You have a question. Why are they responding in that way? But behind your question is a need to make sense of their response. Okay? And that process of making sense in the very ordinary, everyday issues of day-to-day life translate directly into making sense of the knowledge you have to learn. Now, it's a big leap and it's a big, big ask. If I'm trying to make sense out of Bob's behavior, I try to situate it. Right? So, for example, he's angry. That's what I see, right? That's like the facts being poured into you in your lecture. Seeing Bob angry or a lecturer pour tons of data in front of you. That's your basic data, right? That's poured in front of you, the anger. And you need to make sense of it because you want to understand it, you want to learn it. It's true for knowledge and science, and it's true for our friend Bob. Bob's actually a very nice person. And by saying he's a very nice person, we are even more perplexed that they're angry. Okay? To make sense out of the anger, we have to understand the fact as a response to a context of some kind. Now, context isn't necessarily a familiar word for some of you who have not studied perhaps English and the humanities. You may understand the word condition. So let's use we'll use an example from chemistry in a minute, because that provides a very simple image. But we understand his anger when we see it as a response. And what are we seeing it as a response to? We're seeing it as a response. Thank you very much. I've just had a tea interruption. Thank you very much, daughter number 2. We see it as a response to a context. So here's Bob, and we want to make sense out of it. We discover that Bob has just been sacked. So his anger is a response to that situation. Nice and simple. Everyone who is listening to this video will not struggle to understand that. That process we went through, where we took the fact, the anger, which we saw, and then we traced it backwards to see it as a response to a set of conditions or contexts or situations. And as soon as we found a context, a situation which made sense of that anger as a response, it made sense. It makes sense. He got sacked. He's unhappy, right? Not very difficult. In ordinary everyday life, this trivial example gives us an idea of how the brain works. Now we take the same pattern and we extend it to technical scientific knowledge. Okay, so our challenge is that you're coming to learn scientific knowledge, abstract knowledge. Let's let that come into focus. Okay, so we can understand Bob easily. We see what Bob does, we see what our friends do, we see what we do as a response to situations, right? Nice and simple. But now science seems to be a completely different type of thing to understand. I go to a lecture and I hear a lecturer talk about some abstract. Now I need a good example. The tricky thing here is that some of you are doing business information systems, won't do programming. Some of you are confident with some subjects, understand them very well. Some of you don't understand other things that other people understand very well, and so on. Those who understand a subject are able to see it within its context and conditions. The best example I'm going to give is from chemistry that I can possibly provide as a good starting point. Okay, you're not chemists, but all of you should be reasonably familiar or unfamiliar with chemical ideas. When we talk about chemistry and we talk about an element, right, in the periodic table, we often understand what it does as a response to a set of conditions. Okay, the same pattern is here. So let's just say that we're looking at I don't know, not gold. Let's say that we're looking at calcium. Okay, calcium, which in one form is just a white, soft stone, or not stone, soft material. We heat it up. What are the conditions? Temperature, heat, right? Pressure. Some of you may be cringing and thinking, please don't give us any more science. We don't want any more science. But what I'm saying to you is that science also uses the same pattern. We understand the behavior of the calcium, like we understood Bob's anger, as a response to the conditions in which it is or exists. You heat up a blob of calcium, you're changing the conditions in which that calcium exists, and it will respond appropriately. The way it responds is a function of its structure, right? Its chemical bonds, we will say. Okay? Now, for those of you who hate chemistry and have just turned off and say, for goodness sakes, Nad, not chemistry, I thought we got away with chemistry. Let's find another example, one closer to home. Okay, here's my point though, right? The reason we have science, the reason that any of you have studied science and understood science is because it follows the same pattern. We're always understanding stuff in relation to conditions. There are three words here: conditions, contexts, or situations. Okay? And when we look at science, science can get very, very abstract. We look at the property, the structural properties of a particular element, and we understand it and how it behaves, right? Its behavior, it's getting angry, it's getting sad, in this case, melting, transforming, etc., as a response to the conditions in which it is. Let's have another example, right? Let's bring this up. Let's have a look at an example from biology. So in biology, let's take a very crude and simple example. We could take a single-celled organism, or we could take a seed. Okay? A seed, if you leave a seed in certain conditions, I'm going to draw the conditions like that. If the conditions are, I don't know, concrete, dry, the seed doesn't do anything, right? Its response to those conditions is pretty null, right? It might just die very quietly, or might just not. But if you put it in a condition of soil, which is warm, which has certain nutritions, the seed responds to those conditions by turning into a plant. Same concept appears. A seed, which we want to understand, we understand its behavior to turn into here, right? So that's its behavior. That's what it does, right? As a response, always to its conditions. If they're concrete, if you put it on a seed on a piece of concrete, it doesn't do anything. But if you put it in soil with moisture and warmth over a period of time, you will see that it grows into a plant of some kind. So it is responding to its conditions. Right? Absolutely critical. So for chemistry, we have an idea that to understand the behavior of an atom or an element, you have to see its behavior as a response to the conditions in which it is. Its internal structure will determine how it responds, what it does. But what it does, the fact that it does anything, is a function of the conditions. Okay, so let's come up a level. So we've had biology, we've had chemistry. Physics is perhaps a little bit too far and too abstract. So let's have a look at something in computing. Okay. Computing is a fascinating discipline. And what makes computing let's get that into focus. What makes computing really interesting is that it is essentially, the objects of computing are all human artifacts. Okay, now if we're really going to try to understand and help you study computing, we need to have a simple concept like this, right? Computing is different from chemistry or biology because the objects of computing are made by human beings, right? These are human artifacts, whether they're physical computers, whether they're algorithms, right? And let's also include business IT as well. Business information services as well. We've got algorithms, we've got physical devices. They're all human artifacts. Whether we are talking about, algorithms are quite abstract. Okay, some of the things that we create are abstract, like an algorithm. And we take an algorithm and we encode it in some real program or system. But the critical element to understanding and approaching this subject that you are doing, right? To understand it and get your basic frame to help you and accelerate and not waste your time. Okay, so stop wasting your time that you are dealing with something like physics or chemistry or biology. Biology is more complex because it deals with human life in some way. The difference is the objects that you will study, the objects of knowledge, are all human artifacts. Okay, they're also the concept. A concept is also a human artifact. Okay, we make it, we build it, we invent it. We don't discover computers in the forest. Could you imagine? Could you imagine a situation where computing and computers, machinery, and network cables were naturally existing, well, of course we'd understand them differently, right? But it makes a really profound difference to you to see the objects of computing and your study as human artifacts. Now, you might be saying, okay, I get it, human artifacts, things that human beings make, yeah, blah, 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 blah. So what? What difference does that make to me when I'm coming to study it? Well, it makes actually profound difference, because if a human artifact is something a human being makes, right? So the activity of a human being making this or doing something with this artifact is the thing we are trying to understand, then we have to understand this within the conditions and contexts out of which human beings behave, right? So computing, strangely enough, even with programming, it is not a discipline like physics where the basic objects are detached from human life and you're understanding something. You are understanding something about human life and human activity, because it's human activity that generates the knowledge and the objects that you study and that you have to learn. So what we're trying to basically say is that what are the conditions for human beings? What were they responding to build that piece of technology or to come up with that theory or to make that physical device? Now, when I've discussed this, I don't know what that word is, that's device. When I've discussed this with students in the past, what we've all agreed is that you cannot, if you want to really understand computing, you should understand it as a process of purposeful. One of the basic conditions is purposeful human activity. Now, some of you might be saying, oh, come on, computing is technical stuff. It's all about algorithms. It's all about this. No, it isn't. It's all about purposeful human activity. It's humans making things to do things. When humans are making things to do things, they are responding to conditions. What are those conditions? Why did someone invent programming languages? Right? What were the conditions? What was the point of it? What a database is for, right? Before you actually get inside the structure of a particular database, it's stupid and simple, but it's a sensible question to start with. Frame all of your subject areas, networking, databases, information systems, programming, as a response to a set of conditions or purposes. Okay? So ground what you are learning in computing in terms of human beings having a purpose and creating technologies to help them solve and resolve problems. So we come to a very, very interesting model here, that humans solve problems by making things. If you want to understand, now I'm going to take a programming example. If you want to understand why you are studying Python, for those who are studying Python, or if you're a business information systems person, why you might be studying SQL database, or if you're a web designer and you might be studying HTML or JavaScript, what are you trying to make? And if you're trying to make something, what's the purpose behind what you're trying to do? So this might sound to you initially as completely irrelevant and outside your field of study. You might think computing is really a technical discipline and please just give me technical. I would say to you, here's the interesting thing. If chemistry and the natural world operates on this principle that everything, and biology is my nice little, where is it? There's my nice little, put that there as well, right? If everything in the natural order of which we're part is a response to a set of conditions and you want to understand it, from Bob down to seeds, down to single cell organisms, down to human beings, down to technology, it is all about responding to a set of conditions. Then you have a tool to help you decode anything. I'm going to put this here to finish. You have a tool to decode anything you have to study, but it requires a little bit more effort on your part because it's a habit. A good teacher helps you see this relationship of conditions, responding, and objects. A good teacher will show you what the point of the thing that you're studying, the object of your study, as a response and what conditions it came out of. So I'll give you an idea of it to help you get your head around it. But pretty much most of you can understand the basic shape and form of nearly every simple computing advance and what parts of computing are if you just apply this principle. So if you're trying to understand Python, for example, or why is there Python 3.9? That's a specific question rather than 3.8. What is that development a response to? Shortcomings in 3.8. Or was there a parallel development in another programming language to help it work in this context? It's constantly happening, right? It's true for every subfield of computing. So cybersecurity is an obvious easy one, right? You're studying basically human activity and how it manipulates technology to achieve what purpose? What's the point of hacking a system, right? Becomes an ethical question. So, this is huge. The potential for this to help you with your study is absolutely huge. What I would recommend you do is you ask yourself very serious, simple bunch of questions when you study a new topic. What is the object I'm studying, right? As an artifact, as something someone has made as a result of human activity. What's the human activity that brought it about? So let's just say that you're studying hacking behavior from a group of youngsters. Okay, now that activity is purposeful. To understand where it comes about as a function of the conditions of those people. And what are those conditions? One of them might be ideas in their head, right? Or it could have been the condition could have simply been, I wanted to give it a try because I didn't know. Conditions doesn't mean always something objective. It can be ideas, it can itself be theories and concepts. So a concept can be a condition for another condition to emerge. So here, when we talked about a concept map, the relationship between concepts is not some kind of line which links them in some kind of chain-like way. One concept acts as a set of conditions which you respond to, and new concepts emerge. New concepts always emerge in a field of concepts. And when you're trying to learn a subject, you need to get your head around these connections. What are the conditions for that idea to have come about? So if I can just finish on one very last point, right? And that is all concepts are responses to conditions. If it's true for single cell organisms, if it's true for physics, if it's true for planetary science, astronomy, astrology, not astrology, that's not planetary science. What did I say that for? That was a bit of a Freudian slip. It's true for what goes on in the machinery of your brain. In your brain, when you form a concept, that concept is a response to a set of conditions. Part of the conditions are the interactions you have with other people, but critically, they're also a field of other concepts. So we are constantly building up our ideas in relationship as responses to other ideas. So when you're trying to learn a new subject, as this map says, you have to always try your best to try to link it back to other concepts. So I'm going to stop there because I don't know how much of this you're taking in or whether it's making a ton of sense. But my purpose in showing you this research, the result of this most recent research and the work that I've been doing, which you can see examples of it behind, is that the advantage to you from approaching your study in this way is probably going to make the difference between struggling unnecessarily and suddenly using this tool in a simple way, right? You can apply it. So I've got a new concept, a new practice. Understand that practice, understand that concept as a response to a set of conditions. What's the conditions with human beings? Because this is a human field, it's what purpose is it for? But then you might get into the detail, and as you work into the detail, you'll notice the structures on the patterns of our activity themselves are subject to conditions. And this is true for algorithms in particular and computational thinking. But that's for another time. I think for an introductory lecture, I would hope that inspires some of you to question how you approach your study and give yourself a chance to explore a different whole headspace, shall we say. Okay, thank you very, very much for your time, and apologies for the lecture earlier.